Now that we're done with message integrity, we're going to go back and talk about encryption, and we're going to show how to construct encryption schemes that provide much stronger security guarantees than what we had before. But first, let's do a recap of where we are. So in previous segments, we talked about confidentiality, in particular, how to encrypt messages such that we achieve semantic security against what's called a chosen plaintext attack. Now, I kept mentioning again and again that security against chosen plaintext attacks only provides security against eavesdropping. In other words, this only provides security against adversaries that listen to network traffic, but don't actually change any packets or don't inject their own packets, and so on. In this module, our goal is actually to design encryption schemes that are secure against adversaries that can tamper with traffic by blocking certain packets and injecting other packets, and so on. And then we also looked at how to provide message integrity where the message itself is not confidential. We just want to make sure that the message is not modified while it's en route. And so we talked about message authentication codes, MAC algorithms that provide existential unforgeability against a chosen message attack. In other words, even though the attacker is able to obtain the MACs on arbitrary messages of his choice, he can't build MACs for any other messages. And we looked at a number of MAC constructions, in particular a CBC MAC, HMAC, a parallel MAC construction, and a fast MAC construction called a Carter-Wagman MAC. In this module, we're going to show how to combine these confidentiality and integrity mechanisms to obtain encryption schemes that are secure against a much, much stronger adversary, namely an adversary that can tamper with traffic while it's in the network, inject its own packets, block certain packets, and so on. And our goal is basically to ensure that even against such powerful adversaries, we maintain confidentiality. In other words, the adversary can't learn what the plaintext is, and the adversary can't even modify the ciphertext and cause the recipient to think that a different plaintext was actually sent. So before we do that, I want to give you a few examples of adversaries that can tamper with traffic and as a result completely break security of CPA secure encryption. This will show you that actually without providing integrity, confidentiality can also be destroyed. In other words, the two must go together, integrity and confidentiality, if we're going to achieve security against active adversaries. So let's look at an example from the world of networking. In particular, let's look at TCP/IP. I'm going to use a highly simplified version of TCP/IP just so we can quickly focus on the attack and not get bogged down by the details. So here we have two machines communicating with one another. A user sits at one machine and the other machine is a server. Now the server, of course, has a TCP/IP stack that's receiving packets, and then based on the destination field in those packets, it forwards the packets to the appropriate place. So here we have, for example, two processes listening to these packets. A web server, say, over here, and another user, we'll call him Bob, over here. The web server listens on port 80, and here this user Bob listens on port 25. Now when a packet comes in, the TCP/IP stack looks at the destination port. In this case it would be destination 80, and as a result the stack forwards the packets over to the web server. If the destination port said port 25, the TCP/IP stack would forward the packet over to Bob, who's listening on port 25. Now a fairly well-known security protocol called IPsec encrypts these IP packets between the sender and the recipient. So here the sender and the recipients basically have a shared key. And when the sender sends IP packets, those IP packets are encrypted using the secret key K. Now, when a packet arrives at the destination, namely it arrives at the server, the TCP/IP stack will go ahead and decrypt the packet, and then look at the destination port and send it to the appropriate place, decrypted. You notice the data here is decrypted. So in this case, it would send it to the web server because the destination port is port 80. If the destination port happens to be port 25, the TCP/IP stack will decrypt the packet, look at the destination port, and send the data in the clear to the process who's listening on port 25. So now I want to show you that without integrity, in this setup, we can't possibly achieve any form of confidentiality. And let's see why. So imagine the attacker intercepts a certain packet that's intended for the web server. In other words, it's an encrypted packet intended for port 80. Remember that the attacker can actually receive the decryption of any packets that's intended for port 25 because the TCP stack will happily decrypt packets for port 25 and send them over to Bob, who's listening over here. So what Bob is going to do, Bob here is the attacker, what he's going to do is he's going to intercept this packet en route, prevent the packet from reaching the server as is, and instead he's going to modify the packet So now the destination port is going to read like port 25. This is done on the ciphertext, and we're going to see how to do that in just a minute. When this packet now arrives at the server, the destination port says 25, the server will decrypt the packet, see that the destination is 25, and forward the data over to Bob. So now Bob was simply by changing the destination port, Bob was able to read data that was not intended for himself, but rather was intended for the web server. So if the data is encrypted using CBC encryption with a random IV, remember this is a CPA secure scheme. Nevertheless, if that's the case, I'm going to show you that it's trivial for the attacker to change the ciphertext so that now he can obtain new ciphertext where the destination port is 25 instead of 80. The only thing that's going to change is just the IV field. In fact, everything else is going to remain the same. So let's see how to do it. So here, just remind yourself that in fact, what the attacker captured is a CBC encrypted packet where he knows the destination port is port 80, but he doesn't know what the data is. The attacker has no clue what the data is, but he does know this packet is intended for the web server. His goal is to build a new encrypted packet where now the destination port is port 25. So the way he's going to do it, as we said, is just by changing the IV. And let me remind you that the way you decrypt CBC encrypted data is essentially the first plaintext block is simply decryption of the first ciphertext block XORed with IV. And we know that in the original packet, this is going to read dest equals 80, because in the original packet, the destination port is port 80. So now my question to you is, how would the attacker change the IV so now the destination port will read dest equals 25? So it's pretty easy to see that if the attacker simply takes the original IV, XORs it with here, there are a bunch of zeros over here, and a bunch of zeros over here. He XORs it with the zeros, and then 80 XORs with zeros, and then 25 in the appropriate place, namely in the port bytes in the encrypted packet. Then it's easy to see that when this new IV prime is sent along with the original ciphertext, when the attacker decrypts, you can see that the original ciphertext would decrypt to port 80, but now the new IV will cancel out this 80. This 80 here cancels out the 80 that would be obtained in the original plaintext, and then by XORing with 25, essentially the destination now becomes 25. So this is a nice example where, with a simple change to the IV field, the attacker was able to divert the packet so that now after decryption, the packet goes to the attacker instead of the actual web server. And as a result now, the attacker can read the plaintext data that was intended for the server. So this nice example shows that without integrity, it's simply impossible for a CPA secure encryption to provide confidentiality when the attacker can modify packets en route. CPA secure encryption only provides confidentiality if the attacker is only eavesdropping on data but can't actually modify ciphertext en route. Whereas you see, if you can modify ciphertext, a simple modification completely reveals the plaintext. I want to show you another tampering attack that only requires network access to traffic. It doesn't actually require the attacker to be present on the decryption machine. So let's look at an example where there's a remote terminal application where every time the user hits a keystroke, basically an encrypted keystroke is sent over to the server. And let's pretend that the encrypted keystroke is encrypted using counter mode. So here you have the TCP/IP packet. D here corresponds to the 1 byte keystroke, and as we said, it's encrypted using counter mode. And as you probably know, every TCP packet actually contains a checksum. This is a 16-bit checksum that's just used to detect transmission errors. So the server, if it receives a packet that has the wrong checksum, it simply drops it on the floor and ignores it. Now the TCP header, including the checksum and the keystroke, all are encrypted using counter mode. Now the attacker wants to learn what the keystroke was, and let me show you what he can do. The attacker is going to intercept this packet, and he's not actually going to modify it. He's going to send it over to the server, but he's going to record the packet. Later on, he's going to modify the packet and send a modified packet over to the server. What he's going to do is he's going to XOR the encrypted checksum field with a value T, and he's going to XOR the encrypted data field with a value S. And he's going to do this for lots and lots of T's and S's. Now remember, a property of counter mode is that if you XOR the ciphertext with T, after decryption, the resulting plaintext is also XORed with T. Similarly, if you XOR the encrypted data with S, after decryption, the resulting decrypted data will also be encrypted with S. Now, the server is going to decrypt this modified packet, and the resulting packet is going to have the checksum XORed with T and the data XORed with S. Now what happens? If the modified checksum is correct for this modified packet, the server will send an ACK back. If the modified checksum is incorrect for this modified packet, the server will just drop the packet on the floor and do nothing. So the attacker can simply observe, look for an ACK packet or not, and in doing so, he learns whether this particular XOR of T and XOR of S pairs corresponds to a valid checksum or not. Now the attacker is going to do this for lots and lots of T's and S's, and you notice what he learns is if I modify the data by XORing it with this particular value S, that changes the checksum by a particular value T. And he learns this for lots of T and S pairs. So it turns out for certain checksums, by looking at a sequence of equations of this type, you can actually figure out what the value D is. I should point out that for the TCP checksum, this actually might not be true, but certainly there are easy checksums for which this is actually absolutely true. So again, by looking at a lot of equations of this type, the attacker can recover D. And this is a really nice example of what's called a chosen ciphertext attack. The attacker basically submitted ciphertext of his choice that was derived from the ciphertext that he wanted to decrypt. And then by looking at how the server responded, he was able to learn something about the resulting plaintext. And by repeating this for many different values of T and S, he was actually eventually able to recover what the actual full plaintext is. So in this segment, we're going to look at many more examples of attacks of this type. These are called active attacks, where the attacker is actually modifying traffic en route. And I hope that these two simple examples convinces you that all you provide is CPA security, in other words, security against eavesdropping. You can't even guarantee secrecy against an active attacker. Not only does your ciphertext not have integrity, in other words, the recipient might obtain a message different from the one sent by the sender, but you don't even have confidentiality. And I showed you two examples where, without integrity, the attacker can simply decrypt the packet by using the recipient as an oracle for decrypting certain parts of the data. And so the lesson that I'm going to repeat again and again and again throughout this module is that if your message needs integrity but no confidentiality, just use a MAC. But if your message needs integrity and confidentiality, you have to use what's called an authenticated encryption mode, which is precisely the topic of this module. So the next thing we're going to do is define what authenticated encryption means, and we're going to build authenticated encryption systems. But the point I want you to remember is that the CPA security modes we discussed before should never actually be used to encrypt data by themselves. So CBC with a random IV is a building block towards authenticated encryption, but should never be used on its own. Okay, so we're going to define authenticated encryption in the next segment. In the last segment, we saw two active attacks that can completely destroy the security of CPA secure encryption. In this segment, we're going to define a new concept called authenticated encryption that remains secure in the presence of an active adversary. In later segments, we'll construct encryption schemes that satisfy this new authenticated encryption concept. So what is authenticated encryption? Authenticated encryption is a cipher where, as usual, the encryption algorithm takes a key, a message, and absolutely a nonce, and outputs a ciphertext. The decryption algorithm, as usual, outputs a message. However, here the decryption algorithm is allowed to output a special symbol called bottom. When the decryption algorithm outputs the symbol bottom, basically it says that the ciphertext is invalid and should be ignored. The only requirement is that this bottom is not in the message space, so that in fact it is a unique symbol that indicates that the ciphertext should be rejected. Now, what does it mean for an authenticated encryption system to be secure? Well, the system has to satisfy two properties. The first property is that it has to be semantically secure under a chosen plaintext attack, just as before. But now there's a second property, which says that the system also has to satisfy what's called ciphertext integrity. What that means is that even though the attacker gets to see a number of ciphertexts, it should not be able to produce another ciphertext that decrypts properly. In other words, that decrypts to something other than bottom. More precisely, let's look at the ciphertext integrity game. So here, ED is a cipher with message space M. As usual, the challenger begins by choosing a random key K, and now the adversary can submit messages of his choice and receive the encryptions of those messages. So here, C1 is the encryption of M1, where M1 was chosen by the adversary. And the adversary can do this repeatedly. In other words, he submits M2 and obtains the encryption of M2, and so on and so forth. He submits many more messages up until NQ and obtains the encryptions of all those messages. So here the adversary obtained Q ciphertexts for messages of his choice, and then his goal is to produce some new ciphertext that's valid. So we'll say that the adversary wins the game if basically this new ciphertext that the adversary created decrypts correctly, in other words, decrypts to something other than bottom, and it's a new ciphertext. In other words, it's not one of the ciphertexts that was given to the adversary as part of his chosen plaintext attack. And then, as usual, we define the adversary's advantage in the ciphertext integrity game as the probability that the challenger outputs 1 at the end of the game, and we'll say that the cipher has ciphertext integrity if, in fact, for all efficient adversaries, their advantage in winning this game is negligible. So now that we understand what ciphertext integrity is, we can define authenticated encryption, and basically we say that a cipher has authenticated encryption if, as we said, it's semantically secure under a chosen plaintext attack, and it also has ciphertext integrity. So just as a bad example, let me mention that CBC with a random IV does not provide authenticated encryption because it's very easy for the adversary to win the ciphertext integrity game. The adversary simply submits a random ciphertext, and since the decryption algorithm for CBC encryption never outputs bottom, it always outputs some message, the adversary just easily wins the game. Any old random ciphertext will decrypt to something other than bottom, and therefore the adversary directly wins the ciphertext integrity game. So this is just a trivial example of a CPA secure cipher that does not provide authenticated encryption. So I want to mention two implications of authenticated encryption. The first I'll call authenticity, which means that basically an attacker cannot fool the recipient Bob into thinking that Alice sent a certain message that she didn't actually send. So let's see what I mean by that. Well, here the attacker basically gets to interact with Alice and get her to encrypt arbitrary messages of his choice. So this is a chosen plaintext attack. And then the attacker's goal is to produce some ciphertext that was not actually created by Alice. And because the attacker can't win the ciphertext integrity game, he can't do this. And what this means is, when Bob receives a ciphertext that decrypts correctly under the decryption algorithm, he knows that the message must have come from someone who knows the secret key K. In particular, if Alice is the only one who knows K, then he knows the ciphertext really did come from Alice, and it's not some modification that was sent by the attacker. Now, the only caveat to that is that authenticated encryption doesn't defend against replay attacks. In particular, the attacker could have intercepted some ciphertext from Alice to Bob and could have replayed it, and both ciphertexts would look valid to Bob. So for example, Alice might send a message to Bob saying, transfer $100 to Charlie. Then Charlie could replay that ciphertext, and as a result, Bob would transfer another $100 to Charlie. So in fact, any encryption protocol has to defend against replay attacks, and this is not something that's directly prevented by authenticated encryption. And we'll come back and talk about replay attacks in 2 segments. The second implication of authenticated encryption is that it defends against a very powerful type of adversary, namely an adversary that can mount what's called a chosen ciphertext attack. And we're going to talk about that actually in the next segment. In the last segment, we defined authenticated encryption, but I didn't really show you why authenticated encryption is the right notion of security. In this segment, I want to show you that authenticated encryption, in fact, is a very natural notion of security, and I'll do it by showing you that it defends against a very powerful attack called a chosen ciphertext attack. So in fact, we already saw a number of examples of a chosen ciphertext attack. So imagine the adversary has some ciphertext seed that it wants to decrypt. And what it can do is, for example, fool the decryption server into decrypting some ciphertext, but not actually the ciphertext seed. So we already saw some examples of that. If you remember in the first segment, we looked at an adversary that can submit arbitrary ciphertext, and if the plaintext happened to start with destination equals 25, then the adversary is actually given the plaintext in the clear. So that's an example of an adversary that can obtain the decryption of certain ciphertexts, but not all ciphertexts. Another example we saw is an adversary that can learn something about the plaintext by submitting ciphertexts to the decryptor. So we had this example where the adversary submits encrypted TCP/IP packets to the decryption server, and if the decryption server sends back an ACK, the adversary learns that the decrypted plaintext had a valid checksum. And otherwise, the decrypted plaintext didn't have a valid checksum. So this is again an example of a chosen ciphertext attack where the attacker submits ciphertext and learns something about the decryption of that ciphertext. So to address this type of threat, we're going to define a very general notion of security called chosen ciphertext security. So here we're going to give the adversary a lot of power. Okay, so he can do both chosen plaintext attack and a chosen ciphertext attack. In other words, he can obtain the encryption of arbitrary messages of his choice, and he can decrypt any ciphertext of his choice other than some challenged ciphertext. And as I showed you before, this is actually a fairly conservative modeling of real life. In real life, often the attacker can fool the decryptor into decrypting certain ciphertexts for the attacker, but not all ciphertexts. So the model here is that the attacker has a certain ciphertext that it wants to decrypt. It can interact with the decryptor by issuing these chosen ciphertext queries to the decryptor, namely to decrypt various ciphertexts other than the challenged ciphertext. And then the adversary's goal is to break semantic security of the challenged ciphertext. So you notice that we're giving the adversary a lot of power, and all we're asking him to do is break semantic security. So it's going to be fairly difficult to design systems that are secure against such adversaries, and nevertheless we're going to do it. So let's define the chosen ciphertext security model more precisely. So as usual, we have a cipher ED, and we're going to define two experiments, experiment 0 and experiment 1. So this should look somewhat familiar by now. The challenger is going to start off by choosing a random key, and now the adversary is going to submit queries to this challenger. Every query can be one of two types. It can be a chosen plaintext query, or it can be a chosen ciphertext query. So chosen plaintext queries, we already know, basically the adversary submits two messages, M0 and M1. They have to be the same length, and the adversary receives the encryption of either M0 if we're in experiment 0, or M1 if we're in experiment 1. So he receives the encryption of the left or the right, depending on whether we're in experiment 0 or in experiment 1. The second type of query is the more interesting one. This is where the adversary submits an arbitrary ciphertext of his choice, and what he gets back is the decryption of that ciphertext. So you notice the adversary is allowed to decrypt arbitrary ciphertext of his choice. The only restriction is that the ciphertext is not one of the ciphertexts that were obtained as a result of a CPA query. And of course, this wouldn't be fair otherwise, because the attacker can simply take one ciphertext that was obtained from a CPA query. That's going to be either the encryption of M0 or the encryption of M1. If he could submit a CCA query for that particular ciphertext, he will, in response, either obtain M0 or M1, and then he'll know whether he's in experiment 0 or in experiment 1. So this wouldn't be fair, so we say that these CPA ciphertexts that he received are the challenged ciphertexts, and he's allowed to decrypt any ciphertext of his choice other than these challenged ciphertexts. And as usual, his goal is to determine whether he's in experiment 0 or in experiment 1. So I'm going to emphasize again that this is an extremely powerful adversary, one that can decrypt any ciphertext of his choice other than the challenged ciphertext, and still he can't distinguish whether he's in experiment 0 or in experiment 1. So as usual, we say that the cipher is CCA secure, chosen ciphertext secure, if the adversary behaves the same in experiment 0 as it does in experiment 1, namely cannot distinguish the two experiments. So let's start with a simple example and show that in fact CBC with a random IV is not CCA secure, is not secure against chosen ciphertext attacks. So let's see why that's the case. So what the adversary is going to start by doing, he's going to simply submit two distinct messages, M0 and M1, and let's just pretend that these messages are one block messages. And what he's going to get back is the CBC encryption of either M0 or M1. You notice the ciphertext only has one block because the plaintexts were only one block long. Now what is the attacker going to do? Well, he's going to modify the ciphertext C that he was given into C prime simply by changing the IV. Okay, so he just takes the IV and XORs it with 1. That's it. This gives a new ciphertext, C prime, which is different from C, and as a result, it's perfectly valid for the adversary to submit C prime as a chosen ciphertext query. So he asks the challenger, please decrypt this C prime for me. The challenger, because C prime is not equal to C, must decrypt C prime. And now let's see, what happens when he decrypts C prime? Well, what's the decryption of C prime? Let me ask you. So you probably remember from the first segment that if we XOR the IV by 1, that simply XORs the plaintext by 1. So now the adversary received M0 XOR 1 or M1 XOR 1, and now he can perfectly tell whether he's in experiment 0 or in experiment 1. So the advantage of this adversary is basically 1, because he can very easily tell which experiment he's in, and as a result he can win the chosen ciphertext security game. So if you think about it for a second, you'll see that this attack game exactly captured the first active attack that we saw, where the adversary slightly changed the ciphertext that he was given, and then he got the decryptor to decrypt it for him, and therefore he was able to eavesdrop on messages that were not intended for the adversary. So I want to emphasize again that this chosen ciphertext game really does come up in real life, where the adversary can submit ciphertext to the decryptor, and the decryptor can reveal information about the plaintext, or can give the plaintext outright to the adversary for certain ciphertext, but not others. So this is a very natural notion of security, and the question is, how do we design crypto systems that are CCA secure? So I claim that this authenticated encryption notion that we defined before actually implies chosen ciphertext security, and this is why authenticated encryption is such a natural concept. Okay, so the theorem basically says, well, if you give me a cipher that provides authenticated encryption, the cipher can withstand chosen ciphertext attacks. And more precisely, the theorem says the following: if we have an adversary that issues Q queries, in other words, at most Q CPA queries and Q chosen ciphertext queries, then there are two efficient adversaries, B1 and B2, that satisfy this inequality here. So since the scheme has authenticated encryption, we know that this quantity is negligible because it's CPA secure, and we know that this quantity is negligible because the encryption scheme has ciphertext integrity. And as a result, since both terms are negligible, we know that adversary's advantage in winning the CCA game is also negligible. So let's prove this theorem. It's actually a very simple theorem to prove. And so let's just do it as proof by pictures. Okay, so here we have two copies of the CCA game. So this would be experiment 0, and the bottom one is experiment 1. You can see the adversary is issuing CPA queries, and he's issuing CCA queries, and at the end he outputs, a certain guess B, let's call it B prime, and our goal is to show that this B prime is indistinguishable in both cases. In other words, the probability that B prime is equal to 1 in the top game is the same as the probability that B prime is equal to 1 in the bottom game. Okay, so the way we're going to do it is the following. Well, first of all, we're going to change the challenger a little bit so that instead of actually outputting the decryption of CCA queries, the challenger is just going to always output bottom. So every time the adversary submits a CCA query, the challenger says bottom. And I claim that these two games are in fact indistinguishable. In other words, the adversary can't distinguish these two games for the simple reason that because the scheme has ciphertext integrity, the adversary simply cannot create a ciphertext that's not in C1 to Ci-1 that decrypts to anything other than bottom. That is the definition of ciphertext integrity. And as a result, again, because of ciphertext integrity, it must be the case that every chosen ciphertext query that the adversary issues results in bottom. If the adversary, in fact, could distinguish between the left game and the right game, that would mean that at some point he issued a query that decrypted to something other than bottom, and that we could use to then break ciphertext integrity of the scheme. And since the scheme has ciphertext integrity, these left and right games are indistinguishable. Okay, so that's kind of a cute argument that shows that it's very easy to respond to chosen ciphertext queries when you have ciphertext integrity. And the same thing exactly applies on the bottom, where we can simply replace the chosen ciphertext responses by just always saying bottom. Okay, very good. But now, since the chosen ciphertext queries always respond in the same way, they're not giving the adversary any information. The adversary always knows that we're always going to just respond with bottom. So we might as well just remove these queries, because they don't contribute any information to the adversary. But now, once we remove these queries, the resulting game should look fairly familiar. The top right game and the top bottom game are basically the two games that come up in the definition of CPA security. And as a result, because the scheme is CPA secure, we know that the adversary can't distinguish the top from the bottom. And so now, by this chain of reasoning, we've proven that all these games are equivalent, and in particular, the original two games that we started with are also equivalent, and therefore, the adversary can't distinguish the top left from the bottom left, and therefore, the scheme is CCA secure. So this gives you the intuition as to why authenticated encryption is such a cool concept, because primarily it implies security against chosen ciphertext attacks. Okay, so as we said, authenticated encryption ensures confidentiality, even if the adversary can decrypt a subset of the ciphertext. And more generally, even if he can mount a general chosen ciphertext attack, he still is not going to be able to break semantic security of the system. However, it is important to remember the two limitations. First of all, it does not prevent replay attacks on its own. We're going to have to do something in addition to defend against replay attacks. We're going to see several examples where if the decryption engine reveals more information about why a ciphertext is rejected, it doesn't just output bottom, but it actually outputs more information, say by timing attacks, and that explains why the ciphertext is rejected, then in fact that can completely destroy security of the authenticated encryption system. So we'll see some cute attacks like this in a later segment. Okay, so in the next segment we're going to turn to constructing authenticated encryption systems. In this segment we're going to construct authenticated encryption systems. Since we already have CPA secure encryption and we have secure MACs, the natural question is whether we can combine the two somehow in order to get authenticated encryption. And that's exactly what we're going to do in this segment. Authenticated encryption was introduced in the year 2000 in two independent papers that I point to at the end of this module. But before then, many crypto libraries provided an API that separately supported CPA secure encryption and MACing. So there was one function for implementing CPA secure encryption, for example, CBC with a random IV, and another function for implementing a MAC. And then every developer that wanted to implement encryption had to himself call separately the CPA secure encryption scheme and the MAC scheme. In particular, every developer had to invent his own way of combining encryption and MACing to provide some sort of authenticated encryption. But since the goals of combining encryption and MACing wasn't well understood, since authenticated encryption hasn't yet been defined, it wasn't really clear which combinations of encryption and MACing are correct and which aren't. And so every project, as I said, had to invent its own combination, and in fact not all combinations were correct. And I can tell you that the most common mistake in software projects were basically incorrectly combining the encryption and integrity mechanisms. So hopefully by the end of this module, you will know how to combine them correctly and you won't be making these mistakes yourself. So let's look at some combinations of CPA secure encryption and MAC that were introduced by different projects. So here are three examples. So first of all, in all three examples, there's a separate key for encryption and a separate key for MACing. These two keys are independent of one another, and both are generated at session setup time. And we're going to see how to generate these two keys later on in the course. So the first example is the SSL protocol. So the way SSL combines encryption and MAC in the hope of achieving authenticated encryption is the following. Basically, you take the plaintext M, and then you compute a MAC on the plaintext M. So you use your MAC key, KI, to compute tag for this message M. And then you concatenate the tag to the message, and then you encrypt the concatenation of the message and the tag. And what comes out is the actual final ciphertext. So that's option number one. The second option is what IPsec does. So here you take the message. The first thing you do is you encrypt the message, and then you compute a tag on the resulting ciphertext. So you notice the tag itself is computed on the resulting ciphertext. The third option is what the SSH protocol does. So here the SSH takes the message and encrypts it using a CPA secure encryption scheme. And then to it, it concatenates a tag of the message. The difference between IPsec and SSH is that in IPsec, the tag is computed over the ciphertext, whereas in SSH, the tag is computed over the message. And so these are three completely different ways of combining encryption and MAC, and the question is, which one of these is secure? So I will let you think about this for a second, and then when we continue, we'll do the analysis together. Okay, so let's start with the SSH method. So in the SSH method, you notice that the tag is computed on the message and then concatenated in the clear to the ciphertext. Now this is actually quite a problem because MACs themselves are not designed to provide confidentiality. MACs are only designed for integrity. And in fact, there's nothing wrong with a MAC that as part of the tag outputs a few bits of the plaintext, outputs a few bits of the message M. That would be a perfectly fine tag. And yet if we did that, that would completely break CPA security here because some bits of the message are leaked in the ciphertext. And so the SSH approach, even though the specifics of SSH are fine and the protocol itself is not compromised by the specific combination, generally it's advisable not to use this approach simply because the output of the MAC signing algorithm might leak bits of the message. So now let's look at SSL and IPsec. As it turns out, the recommended method actually is the IPsec method because it turns out no matter what CPA secure system and MAC key you use, the combination is always going to provide authenticated encryption. Now let me very briefly explain why. Basically what happens is once we encrypt the message, well, the message contents now is hidden inside the ciphertext. And now when we compute a tag of the ciphertext, basically we're locking, this tag locks the ciphertext and makes sure no one can produce a different ciphertext that would look valid. And as a result, this approach ensures that any modifications to the ciphertext will be detected by the decryptor simply because the MAC isn't going to verify. As it turns out, for the SSL approach, there actually are kind of pathological examples where you combine a CPA secure encryption system with a secure MAC, and the result is vulnerable to a chosen ciphertext attack so that it does not actually provide authenticated encryption. And basically the reason that could happen is that there's some sort of bad interaction between the encryption scheme and the MAC algorithm such that, in fact, there will be a chosen ciphertext attack. So if you're designing a new project, the recommendation now is to always use encrypt then MAC because that is secure no matter which CPA secure encryption and secure MAC algorithm you're combining. Now, just to set the terminology, the SSL method is sometimes called MAC then encrypt, and the IPsec method is called encrypt then MAC. The SSH method, even though you're not supposed to use it, is called encrypt and MAC. Okay, so I'll often refer to encrypt then MAC and MAC then encrypt to differentiate SSL and IPsec. Okay, so just to repeat what I've just said, the IPsec method, encrypt then MAC, always provides authenticated encryption. If you start from a CPA secure cipher and a secure MAC, you will always get authenticated encryption. As I said, MAC then encrypt, in fact, there are pathological cases where the result is vulnerable to CCA attacks and therefore does not provide authenticated encryption. However, the story is a little bit more interesting than that, in that it turns out if you're actually using randomized counter mode or randomized CBC, then it turns out for those particular CPA secure encryption schemes, MAC then encrypt actually does provide authenticated encryption and therefore it is secure. In fact, there's even a more interesting twist here in that if you're using randomized counter mode, then it's enough that your MAC algorithm just be one-time secure. It doesn't have to be a fully secure MAC, it just has to be secure when a key is used to encrypt a single message. Okay, and when we talked about message integrity, we saw that there are actually much faster MACs that are one-time secure than MACs that are fully secure. As a result, if you're using randomized counter mode, MAC then encrypt could actually result in a more efficient encryption mechanism. However, I'm going to repeat this again. The recommendation is to use encrypt then MAC, and we're going to see a number of attacks on systems that didn't use encrypt then MAC. And so just to make sure things are secure without you having to think too hard about this, again, I'm going to recommend that you always use encrypt then MAC. Now, once the concept of authenticated encryption became more popular, a number of standardized approaches for combining encryption and MAC turned up, and those were even standardized by the National Institute of Standards. So I'm just going to mention 3 of these standards. 2 of these were standardized by NIST, and these are called Galois counter mode and CBC counter mode. And so let me explain what they do. Galois counter mode basically uses counter mode encryption, so randomized counter mode, with a Carter-Wagman MAC, so a very fast Carter-Wagman MAC. The way the Carter-Wagman MAC works in GCM is it's basically a hash function of the message that's being MAC'd, and then the result is encrypted using a PRF. Now, this hash function in GCM is already quite fast, to the point where the bulk of the running time of GCM is dominated by the counter mode encryption. And it's even made more so in that Intel introduced a special instruction, PCLM-UL-QDQ, specifically designed for the purpose of making the hash function in GCM run as fast as possible. Now, CCM counter mode is another NIST standard. It uses a CBC MAC and then counter mode encryption. So this mechanism, you notice, uses MAC then encrypt like SSL does. So this is actually not the recommended way of doing things, but because counter mode encryption is used, this is actually a perfectly fine encryption mechanism. One thing that I'd like to point out about CCM is that everything is based on AES. You notice it's using AES for the CBC MAC, and it's using AES for the counter mode encryption. And as a result, CCM can be implemented with relatively little code, because all you need is an AES engine and nothing else. And because of this, CCM actually was adopted by the Wi-Fi Alliance, and in fact, you're probably using CCM on a daily basis. If you're using encrypted Wi-Fi 802.11i, then you're basically using CCM to encrypt traffic between your laptop and the access point. There's another mode called EAX that uses counter mode encryption and then CMAC. So again, you notice encrypt then MAC, and that's another fine mode to use. We'll do a comparison of all these modes in just a minute. Now I wanted to mention that first of all these modes are nonce based. In other words, they don't use any randomness, but they do take as input a nonce, and the nonce has to be unique per key. In other words, as you remember, the pair key comma nonce should never ever repeat, but the nonce itself need not be random, so it's perfectly fine to use a counter, for example, as a nonce. And the other important point is that in fact all these modes are what's called authenticated encryption with associated data. This is an extension of authenticated encryption that comes up very often in networking protocols. So the idea behind AEAD is that in fact the message that's provided to the encryption mode is not intended to be fully encrypted. Only part of the message is intended to be encrypted, but all of the message is intended to be authenticated. A good example of this is a network packet. Think of like an IP packet, where there's a header, and then there's a payload. And typically the header is not going to be encrypted. For example, the header might contain the destination of the packet, but then the header had better not be encrypted, otherwise routers along the way wouldn't know where to route the packet. And so typically the header is sent in the clear. The payload, of course, is always encrypted. But what you'd like to do is have the header be authenticated, not encrypted, but authenticated. So this is exactly what these AEAD modes do. They would authenticate the header and then encrypt the payload, but the header and the payload are bound together in the authentication, so they can't actually be separated. So this is not difficult to do. What happens is in these three modes, GCM, CCM, and EAX, basically the MAC is applied to the entire data, but the encryption is only applied to the part of the data that needs to be encrypted. So I wanted to show you what an API to these authenticated encryption with associated data encryption schemes look like. So here's what it looks like in OpenSSL. For example, just as an API for GCM. So what you do is you call the init function to initialize the encryption mode, and you notice you give it a key and the nonce. The nonce, again, doesn't have to be random, but it has to be unique. And after initialization, you would call this encrypt function, where you see that you give it the associated data that's going to be authenticated but not encrypted. You give it a data that's going to be both authenticated and encrypted, and it gives you back the full ciphertext, which is an encryption of the data, but of course does not include the AAD, because the AAD is going to be sent in the clear. So now that we understand this mode of encrypt then MAC, we can go back to the definition of MAC security, and I can explain to you something that might have been a little obscure when we looked at that definition. So if you remember, one of the requirements that followed from our definition of secure MACs meant that given a message MAC pair on a message M, the attacker cannot produce another tag on the same message M. In other words, even though the attacker already has a tag for the message M, he shouldn't be able to produce a new tag for the same message M. And it's really not clear, why does that matter? Who cares if the adversary already has a tag on the message M? Who cares if he can produce another tag? Well, it turns out if the MAC didn't have this property, in other words, given a message MAC pair, you can produce another MAC on the same message, then that MAC would result in an insecure encrypt then MAC mode. And so if we want our encrypt then MAC to have ciphertext integrity, it's crucial that our MAC security would imply this strong notion of security, which of course it does because we defined it correctly. So let's see what would go wrong if in fact it was easy to produce this type of forgery. So what I'll do is I'll show you a chosen ciphertext attack on the resulting encrypt then MAC system. And since the system has a chosen ciphertext attack on it, it necessarily means that it doesn't provide authenticated encryption. So let's see. So the adversary is going to start by sending two messages, M0 and M1. And he's going to receive, as usual, the encryption of one of them, either the encryption of M0 or the encryption of M1. And since we're using encrypt then MAC, the adversary receives a ciphertext, we'll call it C0, and a MAC on the ciphertext C0. Well, now we said that given the MAC on a message, the adversary can produce another MAC on the same message. So what he's going to do is he's going to produce another MAC on the message C0. Now he has a new ciphertext, C0, comma T prime, which is a perfectly valid ciphertext. T prime is a valid MAC of C0. Therefore, the adversary now can submit a chosen ciphertext query on C prime, and this is a valid chosen ciphertext query because it's different from C. It's a new ciphertext. The poor challenger now is forced to decrypt this ciphertext C prime, so he's going to send back the decryption of C prime. It's a valid ciphertext, therefore the decryption of C prime is the message MB. But now the attacker just learned the value of B, because he can test whether MB is equal to M0 or MB is equal to M1. As a result, he can just output B, and he gets advantage 1 in defeating the scheme. And so again, if our MAC security did not imply this property here, then there would be a chosen ciphertext attack on encrypt and MAC, and therefore it would not be secure. So the fact that we defined MAC security correctly means that encrypt and MAC really does provide authenticated encryption. And throughout all the MACs that we discussed actually do satisfy this strong notion of unforgeability. So interestingly, this is not the end of the story. So as we said before, the concept of authenticated encryption was introduced. Everyone was just combining MACs and encryption in various ways in the hope of achieving some authenticated encryption. After the notion of authenticated encryption became formalized and rigorous, people kind of started scratching their heads and said, hey, wait a minute, maybe we can achieve authenticated encryption more efficiently than by combining a MAC and an encryption scheme. In fact, if you think about how this combination of MAC and encryption works, let's say we combine counter mode with CMAC, then for every block of plaintext, you first of all have to use your block cipher for counter mode, and then you have to use your block cipher again for the CBC MAC. This means that if you're combining CPA secure encryption with a MAC, for every block of plaintext, you have to evaluate your block cipher twice, once for the MAC and once for the encryption scheme. So the natural question was, can we construct an authenticated encryption scheme directly from a PRP such that we would have to only evaluate the PRP once per block? And it turns out the answer is yes, and there's this beautiful construction called OCB that pretty much does everything you want and is much faster than constructions that are separately built from an encryption and a MAC. So I wrote down kind of a schematic of OCB. I don't want to explain it in detail. I'll just kind of explain it at a high level. So here we have our input plaintext here at the top. And you notice that first of all, OCB is parallelizable, completely parallelizable. So every block can be encrypted separately of every other block. The other thing to notice is that, as I promised, you only evaluate your block cipher once per plaintext block. And then you evaluate it one more time at the end to build your authentication tag. And then the overhead of OCB beyond just a block cipher is minimal. All you have to do is evaluate a certain very simple function P. The nonce goes into this P, you notice. The key goes into this P. And then there's a block counter that goes into this P. So you just evaluate this function P twice for every block, and you XOR the result before and after encryption using the block cipher. And that's it. That's all you have to do. And then you get a very fast and efficient authenticated encryption scheme built from a block cipher. So OCB actually has a nice security theorem associated with it, and I'm going to point to a paper on OCB when we get to the end of this module where I list some further reading papers that you can take a look at. So you might be wondering, if OCB is so much better than everything we've seen so far, all these three standards, CCM, GCM, and EAX, why isn't OCB being used, or why isn't OCB the standard? And the answer is a little sad. The primary answer that OCB is not being used is actually because of various patents. And I'll just leave it at that. So to conclude this section, I wanted to show you some performance numbers. So here on the right, I listed performance numbers for modes that you shouldn't be using. So this is for randomized counter modes, and this is for randomized CBC. And you can see also the performance of CBC MAC is basically the same as the performance of CBC encryption. Okay, now here are the authenticated encryption modes. So these are the ones that you're supposed to be using. These you're not supposed to be using on their own, right? These two, you should never ever use these two because they only provide CPA security. They don't actually provide security against active attacks. You're only supposed to use authenticated encryption for encryption. And so I listed performance numbers for the three standards. Let me remind you that GCM basically uses a very fast hash, and then it uses counter mode for actual encryption, and you can see that the overhead of GCM over counter mode is relatively small. CCM and EAX both use a block cipher based encryption and block cipher based MAC, and as a result they're about twice as slow as counter mode. And you see that OCB is actually the fastest of these, primarily because it only uses the block cipher once per message block. So based on these performance numbers, you would think that GCM is exactly the right mode to always use. But it turns out if you're on the space-constrained hardware, GCM is not ideal, primarily because its implementation requires larger code than the other two modes. However, as I said, Intel specifically added instructions to speed up GCM mode, and as a result, implementing GCM on an Intel architecture takes very little code. But on other hardware platforms, say in smart cards or other constrained environments, the code size for implementing GCM would be considerably larger than for the other two modes. But if code size is not a constraint, then GCM is the right mode to use. So to summarize this segment, I want to say it one more time, that when you want to encrypt messages, you have to use an authenticated encryption mode. And the recommended way to do it is to use one of the standards, namely one of these three modes for providing authenticated encryption. Don't implement the encryption scheme yourself. In other words, don't implement encrypt and MAC yourself. Just use one of these three standards. Many crypto libraries now provide standard APIs for these three modes, and these are the ones you should be using and nothing else. In the next segment, we're going to see what else can go wrong when you try to implement authenticated encryption by yourself. So I want to show you how authenticated encryption is used in the real world. So let's use TLS as an example and see how TLS works. So data encryption in TLS is done using a protocol called the TLS record protocol. In this protocol, every TLS record starts with a header. We'll see the structure of the header in just a minute, followed by encrypted data that is sent from one side to the other. In TLS, it so happens that the records are at most 16 kilobytes, and if more data than 16 kilobytes needs to be sent, then basically the record is fragmented into multiple records. Now, TLS uses what's called unidirectional keys, meaning that there's one key from browser to server, and there's a separate key from server to browser. So one key is used for sending messages from a browser to the server, and the other key is used from sending messages from the server to the browser. And of course, both sides, both the server and the browser, know both of these keys. And just to be clear, I'll say the browser will use this key to send data to the server, and will use this key to read data from the server. And the server basically does exactly the same thing, just with the opposite keys. Now these keys, both of these keys, are actually generated by the TLS key exchange protocol, which we're going to talk about in the second part of the course. Right now, I'm going to assume that these keys have already been established. They're known to both the server and the browser, and now the browser and server want to exchange information using those keys. So the TLS record protocol uses what's called stateful encryption, which means that the encryption of every packet is done using a certain state that's maintained inside of the browser and the server. In particular, the state that's of interest to us are these 64-bit counters. Again, there are two 64-bit counters, one for traffic from browser to server, and one from traffic from the server to the browser. These counters are initialized to 0 when the session is first initialized, and they're incremented every time a record is sent. So every time the browser sends a record to the server will go ahead and increment this counter. When the server receives that record, it'll go ahead and increment the counter on its side. And when the server sends a record to the browser, it'll go ahead and increment the second counter. And again, when the browser receives this record, it'll go ahead and increment its copy of this counter. So the state, these two counters, basically the state exists both on the browser and on the server, and it's updated appropriately as records are sent from one to the other and received by the appropriate side. Now the purpose of these counters, as we'll see in just a minute, is to prevent replay attacks, so that an attacker can't simply record a record and then replay it at a later time, because by then the counters would have to be incremented. Okay, so let's look at the details of how the record protocol works. In particular, I'll show you kind of the mandatory cipher suite, which is encryption using AES-CBC and MACing using HMAC SHA-1. Okay, so remember, TLS uses MAC then encrypt, where the MAC algorithm is HMAC SHA-1 and the encryption algorithm is AES-128 in CBC mode. Okay, so let's look at how the browser sends data to the server, which, as I said, is done using the browser to server key. Now, the browser to server key itself is made up of a MAC key and an encryption key. Two separate keys that are, again, as I said, negotiated during session setup. And again, I want to be absolutely clear, there is a separate key for browser to server and a separate key from server to browser, so that overall there are 4 keys. 2 MAC keys and 2 encryption keys, each one used in the appropriate direction. Okay, so here I wrote down the diagram of what a TLS packet looks like. It begins with a header that contains the type of the packet, the version number for the protocol, and the length of the packet. Notice the length of the packet is sent in the clear. Now, when encrypting data, a certain record, the encryption procedure works as follows. Of course, it takes key as input, and it takes the current state as input, and then it works as follows. What it would do is, first of all, is it would MAC the following data. Well, here is the actual payload that's MAC'd, but the header is also MAC'd. And in addition, the counter, the current value of the counter is also MAC'd, and of course, it's all the counter is incremented to indicate the fact that one more record has been sent. Now, the interesting thing here is that even though the value of the counter is included in the tag, you notice the value of the counter is actually never sent in the record, and the reason it doesn't need to be sent in the record is that the server on the other side already knows what the value of the counter needs to be. So it doesn't need to be told in the record what the value of the counter is. It implicitly already knows what it is, and when it's going to verify the MAC, it could just use the value that it thinks the counter should be and verify the MAC in that fashion. Okay, so this is kind of an interesting approach where even though the two sides maintain these counters that function as nonces, there's no reason to send the nonces in the record because both sides actually already know what counters to expect in every record that they receive. Okay, so that's the tag. The tag is computed, as we said, over this triple of data. The next thing that happens is that the tag is concatenated to the data. Remember, this is MAC, then encrypt. So here we computed the MAC. Now we're going to encrypt the data along with the tag. So the header, the data, and the tag are padded to the AES block, and I think we already said that this pad, if the pad length is 5, then the pad is done by simply writing the byte 5 times. So if the pad length needs to be 5, the pad would just be 55555. And then we CBC encrypt using the encryption key. We CBC encrypt the data and the tag, and we do that using a fresh random IV, which is later embedded in the ciphertext. And then we prepend the header, the type, the version, and the length, and that gives us the entire TLS record, which is then sent over to the server. So the grayed out fields in this diagram correspond to encrypted data, and the white fields correspond to plaintext data. So you can see that this is TLS's implementation of MAC then encrypt. The only difference from basic MAC then encrypt is the fact that there is a state, namely this counter is being included in the value of the MAC. And again, as I said, that's done to prevent replays. So let's see why that prevents replays. In particular, let's see how the record protocol decrypts an incoming record. So here comes an incoming encrypted record. And again, the server is going to use its own key that it corresponds to data from browser to server and its own browser to server counter. And the first thing it's going to do is it's going to decrypt the record using the encryption key. After encryption, it's going to check the format of the pad. In other words, if the pad length is 5 bytes, it's going to check that it really is 55555. And if it's not, it's going to send a bad record MAC alert message and terminate the connection so that a new session key would have to be negotiated if more records need to be sent. If the pad format is correct, then removing the pad is really easy. All the server does is it looks at the last byte of the pad, say the last byte is equal to 5, and then it removes the last 5 bytes of the record. By doing that, it strips off the pad. The next thing it's going to do is it's going to extract the tag from the record. So this would be the subsequent bytes inside of the record. So this would be the trailing bytes in the record after we remove the pad. And then it's going to verify the tag on the header, the data, and its value of the counter. And if the MAC doesn't verify, again, it's going to send an alert, bad record MAC, and tear down the connection. And if the pad does verify, it's going to remove the tag, remove the header, and the remaining part of the record is the plaintext data that's given to the application. Now you can see that if a record is ever replayed, in other words, if an attacker records a particular record and then replays it to the server at a later time, then by then the value of the counter would have changed, and as a result, the tag on the replayed record would simply not verify because the tag was computed using one value of the counter, but when the replayed record is received at the server, the value of the counter at the server is different from the value that was used to compute the tag, and as a result, the tag would not verify. So these counters are a very elegant and simple way for preventing replays. And the nice thing about this is because both sides know the value of the counter implicitly, there's never a need to send the counter in the record itself. So the counter itself doesn't increase the length of the ciphertext at all. Now, we already mentioned that this particular approach to authenticated encryption, namely MAC then encrypt using CBC encryption, is in fact authenticated encryption. However, it's only authenticated encryption if no other information is leaked during decryption. And we're going to see some cute attacks on TLS if there is information being leaked during decryption. I should say that this bad record MAC alert basically corresponds to the decryption algorithm outputting this reject symbol, the bottom symbol, meaning that the ciphertext is invalid. And as long as there's no way to differentiate between why the ciphertext was rejected, in other words, the decryptor only exposes the fact that a rejection took place, but it doesn't say why the rejection happened, this is in fact an authenticated encryption system. However, if you differentiate and expose why the ciphertext was rejected, whether it was because of a bad pad or because of a bad MAC, then it turns out there's a very cute attack, which we're going to see in the next segment. What I showed you so far is called TLS version 1.1. It turns out that earlier versions of TLS actually had significant mistakes in it, and as a result, the earlier record protocol is vulnerable to a number of attacks. The first mistake is that the IV used in CBC encryption is predictable. And we said earlier that in CBC, if the IV is predictable, then the resulting CBC encryption is not CPA secure. Well, in this older version of TLS, TLS 1.0 and earlier, the IV for the next record is simply the last ciphertext block of the current record. And as a result, if the adversary can observe the current record, he knows the IV for the next record, and that will allow him to break semantic security of the next record. So the resulting scheme is not CPA secure, but not only is it not CPA secure, in fact there's a very cute attack called the Beast attack that's able to decrypt the initial part of a TLS record simply based on the fact that this scheme is not semantically secure. So I should say that this method of choosing the IV to be the last block of the previous record is called chained IVs, and you should remember that this actually should not be used in practice because it always leads to an attack. Because of this, TLS 1.1 moved to what's called explicit IVs, where every TLS record has its own random, unpredictable IV. And that's fixed the problem. As soon as browsers and servers move to TLS 1.1, this will no longer be an issue. Now, another mistake that was done in TLS 1.0 and earlier enabled what's called a padding oracle, which is something that we're going to talk about in the next segment, where what happened was that if the ciphertext was rejected due to an invalid pad, the server would send back an alert message saying decryption failed. Whereas if the ciphertext was rejected due to a bad MAC, the server would send back a bad record MAC alert. As a result, an adversary who observes the alert sent back from the server can tell whether the pad in the ciphertext was valid or invalid, and this introduces a very significant attack called a padding attack, which we're going to talk about in the next segment. The solution to this in TLS 1.1 was basically to say that instead of reporting decryption failed here, we're going to report a bad record MAC even if the pad is incorrect. And as a result, simply looking at which alert is sent back from the server, an attacker can't tell if the ciphertext is rejected because of a bad pad or a bad MAC. So this tries to mask this information. Now the lesson from this is that when decryption fails, you should never ever explain why. I guess this is something that comes out of networking protocols, where if there's a failure, you want to tell the peer why the failure occurred. Well, in cryptography, if you explain why the failure occurred, that very often leads to an attack. In other words, when decryption fails, just output reject, and don't explain why the reject actually happens, just reject the ciphertext. Okay, so now that we've seen TLS 1.1, let's see a broken protocol. So of course I always like to pick on 802.11b WEP, which pretty much got everything wrong. So let's see how not to provide authenticated encryption. So let me remind you how 802.11b WEP works. Basically there's a message that the laptop wants to send to the access point. The first thing that happens is that the laptop computes a cyclic redundancy checksum on the message and concatenates the CRC checksum to the message. Then the result is encrypted using a stream cipher, in particular RC4. If you recall, the key that's used is the concatenation of an initial value IV that changes per packet and the long-term key K, and then the IV along with the ciphertext are transmitted to the other side. Now, we already saw two problems with this approach. One was if the IV is ever repeated, and in fact it is going to be repeated, then you get a two-time pad attack. And the other problem is that WEP uses very closely related keys. In other words, the key is simply IV concatenated K, and the only thing that changes is the IV. So the key is always fixed, which means that these PRG keys are very closely related to one another. And as we said, the PRG that's used here, RC4, is not designed for this type of use, and it completely breaks if you use it with related keys, and as a result, web has no security at all. What I want to show you is that even the CRC mechanism that's used here in an attempt to provide integrity and prevent an adversary from tampering with the ciphertext, even that mechanism is completely broken, and it's actually very easy to tamper with ciphertexts en route. So let's see how that's done. The attack uses a particular property of the CRC checksum, namely that CRC is linear. What that means is if I give you CRC of M, and I ask you to compute CRC of M XOR P, then it's very easy to do. Basically, you just compute some well-known and public function of Fp, you XOR these two together, and that in fact will give you CRC of M XOR P. So in some sense, the XOR just comes out of the parentheses, and that basically means that CRC is linear. Now here's how the attack works. Suppose the adversary intercepts a particular packet that's destined to the access point. Now the packet says it's destined for destination port 80, and the attacker knows that it's intended for destination port 80, and what he wants to do is modify the ciphertext such that now the destination port will say 25 instead of 80. And maybe the attacker can read messages for port 25, and that's how he actually obtains the actual data in the packet. So recall that the CRC checksum is there to make sure that exactly the attacker cannot change data inside of the ciphertext. But I want to show you that in fact it's really easy to modify data in the ciphertext, and the CRC basically provides no security against tampering at all. So let's see how to do it. Well, what the attacker would do is he would basically XOR a certain value XX into the bytes that represent the 80 in the ciphertext. Now what he'll XOR in will basically be the string 25 XOR 80. And you remember that if I XOR a certain string XX into the ciphertext that was created using a stream cipher, when that ciphertext is decrypted, the plaintext at this position will also be XORed by XX. And as a result, after decryption, the plaintext at this position basically will be the original 80 XOR 25 XOR 80, which gives us 25. Okay, so after decryption, the plaintext at this position will now be 25. The problem is that if that's all we did, then this attack would fail because the CRC checksum would not validate. The CRC checksum was built with 80 as a plaintext, but 25 is a different plaintext and needs a different CRC. But it's not a problem because what we can do is we can easily correct the checksum, the CRC checksum, even though the CRC checksum is encrypted. What we do is we XOR f of XX into the ciphertext at the place where the CRC is supposed to be. And as a result, when the ciphertext is decrypted, what will happen is we'll get the correct CRC checksum after decryption. So the interesting thing that happened here is even though the attacker doesn't know what the CRC value is, he's able to correct it using this linearity property such that when the ciphertext is decrypted, the correct CRC value appears in the plaintext. Okay, so the linearity property of CRC plays a critical role in making this attack works. The end conclusion here is basically that a CRC checksum provides absolutely no integrity at all against active attacks, and it should never ever be used as an integrity mechanism, and instead if you want to provide integrity, you're supposed to use a cryptographic MAC, not an ad hoc mechanism like CRC. Okay, so now we've seen how authenticated encryption is implemented in a real-world protocol like TLS. In the next segment, we're going to look at real-world attacks on authenticated encryption implementations that happen to implement authenticated encryption incorrectly. In this segment and the next, I want to show you two very cute attacks on deployed authenticated encryption systems. But first, let's do a quick recap. So recall that authenticated encryption means that the system provides CPA security plus ciphertext integrity. And authenticated encryption means that we can preserve confidentiality in the presence of an active adversary, and moreover, the adversary can't modify the ciphertext in any way without being detected. We also showed that authenticated encryption prevents these very powerful chosen ciphertext attacks. Unfortunately, authenticated encryption has a pretty significant limitation in that it simply can't help a bad implementation. If you implement authenticated encryption incorrectly, then your implementation will be vulnerable to active attacks. And then we looked at standards constructions. I mentioned these 3 standards that provide authenticated encryption. And I want to point out, when you need to use authenticated encryption in practice, you should just be using one of these 3 standards. You shouldn't try to implement authenticated encryption by yourself. And I hope that the attack that I show you in this segment convinces you that this is not something you should do yourself. Just use one of GCM, CCM, or AEX. However, it's good for you to know that in general, when you want to provide authenticated encryption, the correct way to do things is encrypt then MAC, because then no matter which encryption and MAC algorithms you combine, the result will be authenticated encryption, again, assuming the encryption and MAC algorithm are implemented correctly. Okay, so let's look at a very cute attack on the TLS record protocol, in particular when CBC encryption is used. Let me just briefly remind you that the way TLS decryption works is, first of all, an incoming ciphertext is CBC decrypted. Then the next thing that happens is the implementation will check that the pad has the correct format. For example, if the pad is of length 5, the format should be 55555. And if it's not of the correct format, then the ciphertext is rejected. So this basically checks that the ending of the decrypted record contains the correct pad. And then if the pad has the correct format, then the next thing that happens is that the MAC is checked, the tag is checked. And if the tag turns out to be incorrect, again, the record is rejected. If the tag is valid, then the remaining data is considered to be authentic and is given to the application. So what I wanted to point out is there are 2 types of errors in TLS decryption. One is a padding error and one is a MAC error. And it turns out it's very important that the adversary not be told which of these errors occurred. And let me briefly explain why. So suppose an attacker can actually differentiate the 2 types of errors. In other words, he can tell if a pad error occurred or a MAC error occurred. The result is what we call a padding oracle. Because now imagine the adversary has a certain ciphertext that it intercepted, and it wants to try and decrypt that ciphertext. What it could do is it could take that ciphertext as is and submit it to the server. The server is going to decrypt the ciphertext and then look to see if the pad has the correct format. If the pad doesn't have the correct format, we'll get one type of error. If the pad has the correct format, it's very likely, since this is just some random ciphertext that the adversary concocted himself, it's very likely the MAC will be incorrect, and then the adversary will observe a MAC error. So if the pad is invalid, we'll see a pad error, whereas the pad is valid, we'll see a MAC error. As a result, the adversary, after submitting the ciphertext to the server, the adversary can tell whether the last bytes in the decrypted ciphertext have a valid pad or not. In other words, whether the last bytes in the decrypted ciphertext end with 1 or 22 or 333 or 4444 and so on. So the adversary learns something about the decrypted ciphertext just by submitting the ciphertext to the server. So this is a beautiful example of what's called a chosen ciphertext attack, where again the adversary submits a ciphertext and then he gets to learn something about the resulting plaintext. And now the question is whether he can use that information to completely decrypt a given ciphertext. And I want to show you that a padding oracle can actually be used to completely decrypt a given ciphertext. But before I say that, I want to remind you that older versions of TLS actually leaked the type of error simply in the alert message that was sent back to the peer. Different types of alerts were sent depending on which type of error occurred. As soon as this attack came out, SSL implementations simply always reported the same type of error, so just looking at the alert type wouldn't tell the adversary which error occurred. Nevertheless, there was still a padding oracle. So let me explain why. So this was observed by Canvel et al. Canvel et al. Realized that the way TLS decryption is implemented is, first of all, the record is decrypted, then the pad is checked, and if the pad is invalid, decryption is aborted and an error is generated. If the pad is valid, then the MAC is checked, and then if the MAC is invalid, decryption is aborted and an error is generated. As a result, this causes a timing attack. You realize that if pad is invalid, then the alert message is sent very quickly. And you notice here that in fact you see that within 21 milliseconds the ciphertext is rejected. However, if the pad is valid, then now the MAC needs to be checked, and when it's discovered to be invalid, the alert is only generated at that point. In other words, then in that case, it takes a little bit longer until the alert is generated, and you see that on average this takes about 23 milliseconds. So even though the same alert is sent back to the peer, the adversary can simply observe the time until the alert message is generated. If the time is short, it knows the pad was invalid. If the time is long, it knows the pad was valid, but the MAC was invalid. And as a result, the adversary still has a padding oracle that can tell it whether the pad was valid or invalid. So now let's see how to use a padding oracle. So I claim that if the attacker has a certain ciphertext C, he can completely decrypt that ciphertext just using the padding oracle. So let's see how to do it. And just as an example, suppose he wants to obtain M1. In other words, a decryption of the second block of the ciphertext. So let's see what he would do. So here we have the ciphertext that the attacker intercepted. And this just happens to be the decryption of that ciphertext. And the reason I wrote this down is I wanted you to remember how CBC decryption works. So you should keep in mind that one ciphertext block is directly XORed into the decryption of the next ciphertext block. Okay, so the adversary here wants to basically learn just this part of the plaintext, say. So here's what he's going to do. So first of all, he's going to throw away C2 so that the last block really is just C1, which is the one that he's interested in decrypting. Now let's suppose that he has a certain guess G for the last byte of M1. In other words, he just has a guess for this very, very, very last byte. G is a value between 0 and 255. What the attacker will do is the following. He will XOR the value G XOR 01 into the last byte of the block C0, the previous block. Yes, so all he did is he took the last byte of the previous block and XORed that with his guess XOR 01. Now let's think for just a second and see what happens when this two-block ciphertext is decrypted. Well, C0 is going to get decrypted to whatever it's decrypted to. That's just going to be some garbage that we don't care about. But now when C1 is decrypted, the last byte is going to be XORed with this modified C0, and the result, the last byte of the plaintext is going to be also XORed with this extra value that we stuck into C0. So what goes in here is the actual original last byte in the plaintext M1, but now it gets XORed with G XOR 0x01. So now you see where I'm going with this. If the guess G for the last byte of M1 is correct, then these two guys will cancel one another. Last byte XOR G is just 0. And what we'll get as the last byte of the plaintext is just 0x01. I should mention, by the way, 0x01 just means hex notation for 01. So literally, this is just a 1-byte representation of the number 1. Good. So again, what this means is if our guess for the last byte of M1 is correct, then we get a pad that's well-formed. It's just the number 1. The number 1 is a well-formed pad, and therefore the pad is valid, and the padding oracle will say the pad is valid. If the guess is incorrect, then we'll get a value here that's not equal to 1, and then it's very likely that we have an invalid pad. And as a result, the padding oracle will say the pad is invalid. So again, you see that if our guess for the last byte of M1 is correct, we learn that G was in fact a correct guess, whereas if our guess is incorrect, then we learn that G is an incorrect guess. So what the attacker is going to do is he's going to create his modified ciphertext. You notice he only modifies the second block of the ciphertext. We're going to send this to the padding oracle, and then based on the result of the padding oracle, we learn whether the last byte is equal to G or not. Well, now we can simply repeat this again and again for G from 0 to 255. This basically requires 256 chosen ciphertext queries. Actually, I guess on average we'll only have to do 128 chosen ciphertext queries until we find the right G. And then we learn the last byte of M1. Well, so now we know the last byte of M1. I claim that we can now use the exact same process to learn the second to last byte of M1. Let me ask you, what pad are we going to use to learn the second to last byte of M1? Well, it shouldn't be surprising that instead of just using the pad containing the byte 1, we're going to use a 2-byte pad containing the bytes 22. That's a well-formed pad. And now we can always make sure, because we know the last byte of M1, when we do our XORing trick, we can always make sure that the last byte of the plaintext is in fact 02. And now we can guess the second to last byte of M2 by simply trying lots of values in G until we find one that makes the pad in fact be 0202. And by issuing 256 additional queries to the padding oracle, we will get to learn the second to last byte of M1. And now we can iterate this again and again, and basically since the length of the block is 16 bytes, after 16 times 256 queries, we get to learn all of M1. So this is a pretty significant attack that is able to decrypt blocks of the TLS record. So those of you who know the inner workings of TLS should complain that this attack isn't going to work. The problem is that when TLS receives a record with a bad pad or a bad MAC, it shuts down the connection and renegotiates a new key. As a result, the attacker is now stuck with a ciphertext encrypted using an old key, and that key is no longer used anywhere, so it cannot submit any more queries. So with TLS, basically, it can only submit one query, and that's it. Even a single query still leaks information about the plaintext to the attacker, but it doesn't expose the entire plaintext blocked M1. However, this attack is so cute that whenever there's a mistake like this in a protocol, there will be some settings in which it comes up, and in this case, the setting is in the case of an IMAP server. So IMAP is a popular protocol for reading email from an IMAP email server, and it's very common to protect the IMAP protocol by running it on top of the TLS protocol. Now, it turns out in IMAP, every 5 minutes, the IMAP client will connect to the IMAP server and check whether there's new email. And the way it does it is by first logging in to the IMAP server by sending this login username password message, and then it goes ahead and checks if there's new email available. Well, what this means is that every 5 minutes, the attacker gets an encryption of exactly the same message. In particular, it gets an encryption of the password. And so every 5 minutes, it can mount one guess on the block that contains the password. And so if your password is 8 characters long, the attacker simply needs to recover those 8 characters, and he's going to recover them 1 byte at a time by doing one guess per 5 minutes. And so Canville et al. Showed that within a few hours, you can basically recover the user's password just by mounting one guess every 5 minutes. So this is a pretty significant attack against an implementation of TLS, and the defense against this was to always check the MAC whether the pad is valid or invalid, and as a result, it takes the same amount of time to respond whether the pad is valid or invalid. So this removes the timing attack and makes this attack much harder to mount. So there are 2 lessons here. First of all, you notice that if TLS had used encrypt then MAC rather than MAC then encrypt, then this whole issue would be completely moot, because in encrypted MAC, the MAC is checked first, and only then does decryption and pad checking take place. In encrypt and MAC, the ciphertext is discarded because the MAC is invalid, and we never even get to a pad check. As a result, any tampering or games with a ciphertext will be discarded immediately because the MAC is simply going to fail. The second lesson to remember is that, remember I told you that MAC then CBC actually does provide authenticated encryption, but only if you don't reveal why decryption failed. In this case, the padding oracle completely destroyed the authenticated encryption property, and basically I showed you an attack that shows that now this mode does not provide authenticated encryption. So let me ask you the following question. Suppose in TLS, instead of using MAC then CBC, TLS did MAC then counter mode encryption. Would the padding oracle attack still be possible or not? The answer is it wouldn't be possible, simply because counter mode doesn't use any padding at all. So this padding oracle attack only affects CBC encryption modes in TLS. TLS also supports counter mode encryption, and counter mode encryption modes are simply not affected by these padding attacks. So that's the end of this segment. In the next segment, I want to show you another very, very clever attack on authenticated encryption systems. In the last segment, we looked at a padding oracle attack that completely breaks an authenticated encryption system. I hope this attack convinces you that you shouldn't implement authenticated encryption on your own, because you might end up exposing yourself to a padding oracle attack or a timing attack or any other such attack. Instead, you should be using standards like GCM or any other of the standardized authenticated encryption modes as implemented in many crypto libraries. In this segment, I'm going to show you another very clever attack on an authenticated encryption system, and I hope after you see this attack, you'll be completely convinced not to invent and implement your own authenticated encryption systems, but instead always use one of the standard schemes like GCM or others. So this particular attack that I want to show you is an attack on the SSH binary packet protocol. So SSH is a standard secure remote shell application that uses a protocol between a client and the server. It has a key exchange mechanism, and once 2 sides exchange keys, SSH uses what's called the binary packet protocol to send messages back and forth between the client and the server. Now here's how SSH works. So recall that SSH uses what we called encrypt and MAC. Okay, so technically what happens is every SSH packet begins with a sequence number, and then the packet contains the packet length, the length of the CBC pad, the actual payload follows, then the CBC pad follows. Now this whole red block here is CBC encrypted also with a chained IV, so this is also vulnerable to the CPA attack that we discussed before. But nevertheless, this whole red packet is encrypted using CBC encryption, and then the entire clear text packet is MAC'd, and the MAC is sent in the clear along with the packet. So I want you to remember that the MAC is computed over plain text packet, and then the MAC is sent in the clear. This is what we call encrypt and MAC. And we said that this is not a good way to do things because MACs have no confidentiality requirements, and by sending the MAC of the clear text in the clear, you might be exposing information about the clear text. But this is not the mistake that I want to show you here. I want to show you a much more clever attack. So first, let's look at how decryption works in SSH. So what happens is, first of all, the server decrypts the encrypted packet length field only. So it only decrypts these particular first few bytes. Then it will go ahead and read from the network as many bytes as specified in the packet length field. It's going to decrypt the remaining ciphertext blocks using CBC decryption. Then once it's recovered the entire SSH packet, it will go ahead and check the MAC of the plaintext and report an error if the MAC happens to be invalid. Now the problem here is that the packet length field is decrypted and then used directly to determine the length of the packet before any authentication has taken place. In fact, it's not possible to verify the MAC of the packet length field because we haven't recovered the entire packet yet, and as a result we cannot check the MAC. But nevertheless, the protocol uses the packet length before verifying that the MAC is valid. So it turns out this introduces a very, very cute attack, and I'm only going to describe a very simplified version of this attack just to get the idea across. So here's the idea. Suppose the attacker intercepted a particular ciphertext block, namely the direct AES encryption of the message block M, and now he wants to recover this M. And I emphasize that this intercepted ciphertext is only one block length. It's one AES block. So here's what the attacker is going to do. Well, he's going to send a packet to the server that starts off as normal. It basically starts off with a sequence number, and then he's going to inject his capture ciphertext as the first ciphertext block that's sent to the server. Now what is the server going to do? The server is going to decrypt the first few bytes of this first AES block, and he's going to interpret the first few bytes as the length field of the packet. The next thing that's going to happen is the server is going to expect this many bytes before it checks that the MAC is valid. And so what the attacker is going to do is he's going to feed the server one byte at a time. So the server will read one byte and then another byte and then another byte. Eventually the server will read as many bytes as the length field specifies, at which point it will check that the MAC is valid. And of course the attacker was just feeding the server junk bytes, and as a result the MAC is not going to verify and the server will send a MAC error. But you realize that what happened here, the attacker was counting how many bytes it sent to the server, and so it knows exactly how many bytes were sent at the time that it receives the MAC error from the server. So that tells it that the decryption of the first 32 bits of its ciphertext C are exactly equal to the number of bytes that were sent before it saw the MAC error. So this is a very clever attack. So let me say it one more time to make sure this is clear. So again, the attacker has a one block ciphertext C that it wants to decrypt. And let's pretend that when C is decrypted, the 32 most significant bits of the plaintext happen to be the number 5. In this case, what the attacker will see is the following behavior. The server is going to decrypt the challenge block C, and he's going to obtain the number 5 as the length field. So now the attacker is going to feed the server one byte at a time, and after the attacker feeds the server 5 bytes, the server says, hey, I've just recovered the entire packet, let me check the MAC. The MAC is likely to be false, and then it will send bad MAC error. So after 5 bytes are read off the network, the attacker is going to see a bad MAC error, and then the attacker learns that the most significant 32 bits of the decrypted block is equal to the number 5. So there. So he just learned the 32 most significant bits of C. So this is a very significant attack because the attacker just learned 32 bits of the decrypted ciphertext block, and since he can apply this attack to any ciphertext block he wants, he can basically learn the first 32 bits of every ciphertext block in a very long message. So what just happened here? Well, there are actually two things that were wrong in this design. The first one is the decryption operation is non-atomic. In other words, the decryption algorithm doesn't take a whole packet as input and respond with a whole plaintext as output or with the word reject. Instead, the decryption algorithm partially decrypts the ciphertext, namely to obtain the length field, and then it waits to recover as many bytes as needed, and then it completes the decryption process. So these non-atomic decryption operations are fairly dangerous, and generally they should be avoided. In this example, this non-atomic decryption happens to break authenticated encryption. The other problem that happened is that the length field was used before it was properly authenticated, and this is another issue that should never be done. So a decryption field should never be used before the field is actually authenticated. So let me ask you, if you had the option of redesigning SSH, what is the minimum change you would do to make SSH resist this attack? And let me tell you that multiple answers might be correct. One option is to send the length field in the clear, just as in the case of TLS. In this case, there's no opportunity for an attacker to submit chosen ciphertext attack because, well, the length field is never decrypted, and so there's no decryption taking place that the attacker can abuse. Replacing encrypt and MAC by encrypt then MAC doesn't have any impact because this attack would apply either way. The problem is that the length field is used before it's authenticated, and that would have to happen either way. So a better mode of encryption doesn't actually help. Another option is to MAC the length field separately so that now the server can read the length field, check that the MAC for just the length field is valid, and then it would know how many subsequent bytes to read before checking the MAC field on the entire packet. The last option is actually one that works but is terribly inefficient. It would expose the server to a denial of service attack, so I'm not going to mark it as a valid answer. So the main lesson to remember is don't implement or design your own authenticated encryption system. Just use the standards like GCM. But if for some reason you can't use the standards and you have to implement your own authenticated encryption system, then use encrypt then MAC, and make sure not to repeat the mistakes of the last two segments, namely don't use a length field before the length field is authenticated, and more generally don't use any decrypted field before that field is authenticated. Okay, so this is the end of our discussion of authenticated encryption. I wanted to point out a couple of papers on authenticated encryption that you could use as further reading. The first one is a very cute one on the order of encryption and authentication that talks about whether one should do encrypt then MAC or MAC then encrypt, and it shows that one is correct and one is incorrect. It's a good read and there's a lot of information in that paper. The second paper discusses OCB mode, which is a very efficient way of building authenticated encryption. In particular, it looks at a variant of OCB with associated data, as we discussed when we described OCB. The last three papers are attack papers. The first one describes the padding oracle attack that we discussed in the last segment. This one here describes the length attack that we just described in this segment. And the last one describes a number of attacks on encryptions that just use CPA security without adding integrity. So this last paper actually provides a number of good examples for why CPA security by itself should never, ever, ever be used for encryption. Remember, the only thing you're allowed to use is authenticated encryption for confidentiality, or if all you need is integrity with no confidentiality, then you just use a MAC.